that, kind of go next to what our problem is about. So, oh, my iPad so I can write on this. So we've modeled it. Awesome. That's part A. Next part of what we're going to be doing is this proportional controller aspect. So kind of going into what a proportional controller is. If you ever heard of PID controller, many majors of engineering use this type of controller to control literally everything. So it stands for a proportional integral derivative controller, but the controller we're concerned about is just the proportional controller. It's sort of just a simpler version of that. Doesn't have that ID part, that integral derivative aspect. So it's just a proportion based on how it works is works on based on an error between our expected result, a set point, or I guess our expected result and actual result. And based on that error, depending on the sensitivity of this controller, the controller proportional controller constant, it is going to change. I guess in this case, change our inlet flow based on, I believe it is our third tank. So it's a proportional controller based on the set point for the third tank. And what we're going to be doing, well, why is it important? How does it work? And why does the sign matter? Sort of try to find for different KC values. I'll get into. So let's kind of just put this in. First off, I guess I should. So kind of to start out, where will we be coding this in? So the main difference is with the proportional controller now. Say yes. So instead of just having predefined Q inlet flow, we're going to be changing our inlet flow based on the height of the third tank. So I'm actually just going to put that in here in our function. And the reason I can do that is when the function is ran, or when I call the function, it looks locally for the next stored variable. It won't have to look up previously to this line of code, this box of code. You can just define it here so that I don't have to update this. But really, it shouldn't matter as long as you're consistent. So what I'm going to do is, let's see, our inlet flow, Q in, is equal to, now it's not just this constant of 0.75, it's going to depend on our initial flow, and that is, our initial flow is being modified by our proportional constant. And what is that proportional constant? Their equation, I believe, I don't know what the best way to showcase this is. Yes, a PID controller. So if you can kind of see that, I don't know if that might be too hard to see. Something like this. So we're looking only at, kind of see the three different parts broken up, but we're only looking at this first term, the proportional constant part. So with respect to time, again, I believe I mentioned earlier, but proportional controller has to do with this proportional constant Kp, or Kc, I've seen it as Kc as well, times our error. So we're going to go ahead and define that. So I'll call it Kc, our proportionality constant times our error. And since we haven't defined those variables, we'll need to go ahead and define that now. So what is our error? Well, our error is what our set point will be, or what our set point is, and the difference between what our set point is with our current actual result. So I'll go something like, I guess we'll kind of showcase why the sign matters now as well. So be the height of tank 3 minus the height set point that we set for height, the tank 3. The height of tank 3, excuse me. Okay. So we've defined E, the error. We should go ahead and define Kc as well. And we should also define our set point as well. So I believe the problem asks us for a 10% increase. So this is why the height matters. So the sign matters. So if we ask for a 10% increase, that is a 10% increase from our current height, our initial height. And we should be okay putting the function out here because we called it up here. The order does matter in our coding. We need to make sure we don't call a variable that we haven't defined yet. Kind of learned that from firsthand experience. And then KC is so that's the proportionality constant. It's basically how sensitive our controller will be to when it does receive that, it notices that change from our set point. So go with like 1 for now. But I'll go ahead and explain the reason for the set point difference here. So the reason why sign matters so much for the proportionality constant, kind of think this through. Our error is the difference between these three, or our two heights. So we have our height of the tank currently, and our set point. Well, our set point is currently 10% of our initial height. So if we have a height in our third tank that's higher than our set point, how are we wanting to kind of reach our set point? We're going to have to decrease our inlet flow, if that makes sense. The inlet flow is what's controlling all the heights of the tanks. So if the height in the tank 3 is too high, you're going to want to decrease that because it's higher than the set point. How else are you going to go down? You need to decrease our inlet flow. So what's happening right now is if our height is too high and our set point is lower than that, this error will be a positive number. But what's actually happening is that if E, our error, is a positive number, and obviously KC is also a positive number, if that is in addition to our inlet, then that's also a positive number. Meaning that if our height was too high, our inlet would continue remaining positive, which is not what we want to do. The sign matters here in this case. Well, actually, the difference is that it's sort of, how do you want to say this? It doesn't really matter, the difference that's being subtracted here. I could keep it as this, but then put a negative in our proportionality constant. But in terms of standards, it's kind of, for me at least, a little weird to do that. So we're going to go ahead and keep our proportionality constant positive, so we don't have a negative one, even though it's okay to do that. But just for our sakes, for the sign matters, I'm going to do a little flip here so that when we do have a difference, our error is positive, such that negative, so that if our set point is lower than our height of the third tank, the error will be negative, turning this term, the proportionality constant times E, which is our overall proportionality constant controller representation, that term will become negative, resulting in a change inlet flow that is smaller than our initial steady state flow. That makes sense. Hopefully that makes sense. Okay, so let's just go ahead and run that. See what happens. So nothing yelling at me yet. That works. See how that changes. Okay. What does this mean? So I don't want to zoom in here. There's actually no change. Wow, that's okay. So obviously there's something funky is happening here. So we have our tank 1 height is going extremely high, and our tank 2 height is going negative. So what is happening here? I believe our proportionality constant controller, or no. Well, let's just kind of, we're at 300. Oh yeah, wow. Okay, so even at a time span of 300, we're seeing this. So that means our proportionality constant controller is so strong that it is increasing the height so much that in order to kind of match that height, our tank 2 height is going negative, which does not make any sense. So that is kind of attributed to our algorithm's error so far, or I guess we can attribute it to our proportionality controllers like sensitivity. Let's go a lot smaller, like 1e to -6. Evaluate that again. Okay, we got some wiggles. So actually, I don't know, kind of following like a sine cosine function here, trig function. Let's kind of increase our time span so we kind of see more of this. 3000. Okay, wow. So we got a lot of wiggles. But it does look like it comes to sort of like constant, I don't know how you want to call this, constant, I don't know, constant wiggle. So it does change, but we need to remember that our what we're trying to reach for is we have our height set point at a certain number, 22, and wow, we are not hitting that at all. So we're actually only hitting 20.4. So maybe you think increasing our sensitivity will kind of let us hit that height. I don't know. So I think 1 was too much. So I don't know, 1e to negative 3. Oh man, even we are increasing, but we are not hitting. Well, tank 3 keeps on oscillating so much, and we're only hitting 20.4. And these oscillations are important. I will comment that in a second, but let's just kind of see how far our sensitivity and our controller will take us. Yeah, keep on oscillating. That is crazy. So I think you kind of see the point. We're just gonna have so many oscillations, and it's just, yeah, kind of going back to my comment earlier, explain what that is now. So remember, solve IVP, we have many parameters here, but we have this certain parameter. The method is the way it's calculating our differential equation, our nonlinear first order differential equation. So it's using this RK45 method. And right now we're kind of seeing some wiggles that might be artifacts of errors in that calculation method. So what we're gonna have to do is, these are the lists of all those methods. We're gonna change it to Radu, the method of Radu, and see, hopefully that kind of fixes this oscillation error that's occurring. Because if you think about oscillations, the reasons why they're happening is due to the fact that every time we hit a, let's say we're trying to increase our set point, right? So in height, the height in tank 3 reaches its set point at a certain time, but then our inlet flow has to change, right? So when, say, we've increased our inlet flow, or we've let our height reach that, the height of tank 3 reach that height set point that we had, we need to decrease our inlet flow. But by the time we decrease that inlet flow, there's still height, or I guess liquid, still moving through the tanks that will keep on increasing that tank, or the height of tank 3. So maybe you get to a point where you've turned your inlet flow all the way off, but your tank in height 3 is still going. And this kind of continues for a while until you say, hey, I've decreased my inlet flow so much. Why is the height in tank 3 not responding? Well, remember, there was that time delay. And that was the same for earlier when we didn't even have the proportionality constant. So hopefully we kind of fix this with the method, or at least get something closer to our intended result. Let me check where this method was before dense output. So you will want to make that before. I don't think that. Boy, and now it is a string. So we'll do our single quotation mark Radu. Fun to say, Radu. Okay, so yeah, no more oscillations. That's pretty cool, actually. So yeah, no artifacts of those round off errors, simply by changing the method of that calculation. But remember, I didn't changing the method of the calculation doesn't mean that there is no time delay anymore. Since we can also keep changing our proportionality constant to see where the sort of method of Radu kind of hits its limit. So Radu, kind of give context, Radu is more accurate, at least for solve IVP. It's most accurate calculation. I guess this is integration method for solving differential equations that solve IVP has. So it's the most accurate one. But we will see if we keep on changing our KC proportionality constant. We make sure doing what I'm saying we're supposed to do. So for different KC values, yes, we're going to change, or at least simulate the response at this 10% increase. And eventually we will see that it will oscillate perpetually. So right now we're at 1e to negative second. No proportionalities there, or no oscillations yet. I wonder if 1 is still too much. Oh wow, so we now have a 0 in our square root, meaning again, when it was going to 0 before, when you saw tank 1 going super, super high and tank 2 going super, super low, now we're evaluating that function and the square root is 0. So that means, again, too high here. We did 1e to negative second. We can do 0.1. Yeah, so now we got some oscillations here. Same thing. I don't think we are hitting our target. Oh, no, we do hit our target. Or overshooting our target. So yeah, oscillations are getting smaller and smaller. We still don't hit our target here at 22. Yeah. And we're off by 0.4 meters, but still not the best of what it could be. But yeah, we're gonna start seeing these oscillations even as we try to increase our proportionality constant. Trying to find a sweet spot. Oh, keep oscillating here. I wonder what point breaking limit is. Oh yeah, oscillations are killer here. So now we're still overshooting it, but it's trying to even it out as you go from 23, and we're going to, sorry, just checking the time. 23 and decreasing to 22.6. So we're still overshooting. I wonder if we can kind of see if it does even out a little. 22.1. So yeah, it's crazy oscillations, and that lasts for 8,000 seconds. Jeez. Oh. So I guess the point we're trying to make here is that even with the proportionality constant controller, no matter how you're trying to fine tune it, we could keep doing this all day, but inevitably we will not reach our desired set point. And that is because of our time lag, as mentioned. So hopefully in another video, this might get explained. So look forward to that. But I believe we've gone through all both parts of each part, and hopefully you learned a lot, because I sure did trying to troubleshoot all this code. So that's that. I'll look forward to the other parts for this 3 tank height problem or something similar. All right. Thank you.